Matt Leifer, welcome to the podcast.
Thank you.
I'd like to start by asking you some questions so that the audience get to know you both as a person and as a scientist.
Okay.
First, what is something you are glad you have done as a person?
What's something I'm glad I've done as a person?
Yeah, something that makes you proud of?
Well, I mean, the first thing that comes to mind is my kids, the kids that I'm raising. They take up a lot of my life these days. They give me a lot of joy in my life these days.
Nice. Now, as a scientist,
yes,
what is something you are glad you have done as a scientist?
There's lots of things. I mean, it's kind of hard to pick just like one thing. Although there is there is a time when I sort of felt like I had a eureka moment, right? So, it doesn't happen very often, but, a time where you sort of suddenly go from not understanding something to just feel like you fully understand it. And that was essentially probably my most cited paper at the moment is the one on the no broadcasting theorem in generalized probabilistic theories. So as a whole, I was involved in bringing in the sort of generalized probabilistic theories framework to study questions about what's responsible for the information processing power of quantum mechanics, right? So you need a framework to talk about that, which, if you want to answer that question, you have to say, well, what would it be like if it wasn't quantum mechanics, right? So that's where, I mean, this is an old framework, comes from about the 1970s, but we brought it into this study, and basically, things were cleaned up, but basically, I came up with a basic idea for how to prove the no broadcasting theorem in this framework, based on a paper by Goran Lindblad, which was he did the quantum mechanical version of this argument. So that was kind of a eureka moment. I remember Alex Wills was visiting at the time. He was one of the co-authors, and I remember sort of rushing down to his office to explain the proof.
Nice. So I think that there are two keywords I gathered. First, it's information processing, and second, it's quantum physics.
Yes.
How would you characterize your main research interest? Are these two keywords accurate?
Yeah, so I mean, my main research interest is trying to understand just what it is that quantum mechanics is telling us, right? What is it telling us about reality? But I happen to come into this field at a time when quantum information was beginning to blossom. So the whole idea of quantum communication, quantum computers, and it was exciting at the time because it seemed like it's still exciting, but for the first time, it seemed like these more esoteric aspects of quantum mechanics, like entanglement, were actually going to have some practical applications, direct practical applications of things like violations of the Bell inequality, which show you, the weirdness of quantum mechanics pretty directly. So, at the time, I was faced with a decision: do I go into this sort of practical area, applying these things, or do I, stick with the foundations? And I decided to go with the more practical thing for my PhD. So I did my PhD in basically in entanglement theory, but I was always motivated to do it because I wanted to understand quantum physics. And I happened to be lucky because there were also a bunch of other people who were interested in that in the quantum information community, and people thinking that this sort of information theoretic view on things had something to contribute to the foundations.
Let's imagine the future, say 50 years from now.
Yeah.
And many problems will be solved. Many problems are still open. What is if you're allowed to pick one question that's solved, and you know the full answer to this question, what would you pick?
Wow. I mean, I would really like to know the correct interpretation of quantum mechanics, of course. But that's a big thing, right? in perhaps a minority of physicists, I think that there is such a thing as a correct interpretation.
One portal maybe to that prospect would be to reason deeply is about reality. And
Yes.
in particular, one could ask, is the external reality fundamental? This kind of question is particularly fueled by some recent interests in Wigner's friend thought experiment, which you have written about and talked about. Last year, you put a paper on arXiv, which is a review paper on, the title is A Review and Analysis of 6 Extended Wigner's Friend Arguments. First of all, perhaps we should draw a distinction between Wigner's original thought experiment and the recent works, because in your paper you mentioned that they're different. How about you start by telling us your understanding of Wigner's original thought?
Yeah, well, actually, Wigner's original thought experiment, it has an interesting provenance because the way it's discussed these days is fairly different from the way it was discussed when Wigner introduced it, which I think was either in the late 1950s or 1960s. So he wrote a paper, which was basically, the paper was about the mind-body problem, right? So he said, well, one of the reasons why people don't believe in sort of mind-body dualism is because in physics, if something acts on something, then we expect that thing to be able to act back, right? People would make the argument, okay, the laws of physics are kind of a closed system. It's just the system of equations. If you have something else called consciousness that you think doesn't arise from the physics, but is on top of that, then, physics is going to do what it does anyway, right? So there's no sort of way in which that thing can act back on physical reality. So, but what Wigner said is, well, maybe it does act back. What about in quantum mechanics, where we have the collapse of the wave function? So he said, well, perhaps when I become consciously aware of the outcome of a measurement, that in some sense pushes back on the world because it causes the quantum state to collapse to one of a definite measurement outcome. So to make this point sort of more vivid, he introduced the friend experiment. Now, a lot of people are familiar with the idea of the Schrodinger's cat experiment, right? So Schrodinger puts his cat inside a box along with some quantum device that's going to end up in a superposition of two outcomes. By doing a quantum measurement inside the box, and depending on the outcome of the measurement, a vial of poison would be untouched or it would be broken. So you would end up, if the whole thing is an isolated system, in a situation where you have a quantum superposition of the cat being alive and the cat being dead. And Schrodinger said, look how ridiculous that is. This shows us that this description cannot be universally valid. So in Wigner's experiment, instead of putting a cat in the box, he put his friend. Now, the vial of poison is gone, fortunately, because he wouldn't really be much of a friend if he kept that. So instead of that, it's just you put your friend inside a sealed, isolated box. Inside is a quantum particle and the measuring device, which has one of two outcomes. And so the friend performs the measurement, records his outcome. Now, because the box is isolated, Wigner, who is outside the box, just like Schrodinger describes his cat, he would describe the friend inside the box as being in a superposition, an indefinite state where he's neither seeing one thing or the other. So Wigner says, well, obviously, that doesn't happen to conscious people, right? Every time we've ever done a measurement, either we see one outcome or the other outcome. In the case where it's a friend, in the case where it's something that we really know has conscious experience, that should have caused the wave function to collapse. So in this case, he entertained the possibility that the collapse of the wave function was an agent or an observer's consciousness acting back on the world. It's not the popular view, And it's not the way the argument is presented these days, but that was the original argument. So these days, most people tend to think that quantum mechanics, at least so far as we can tell, quantum mechanics, the basic rules of quantum mechanics are universally valid. We haven't discovered ever something which cannot be given a description according to quantum mechanics. Now, maybe there is such a thing, but we just don't know it yet. So we take the hypothesis by means of an assumption that suppose quantum physics really can describe the entire universe, then Wigner really ought to be able to describe his friend as being in this superposition. So in modern times, people don't really want to say that consciousness is what causes the collapse of the wave function. You may want to think that it's more of a sort of effective description, but it doesn't really, nothing really actually collapses. If you want to take that kind of viewpoint, then you have to somehow reconcile the fact that you think that the observer inside the box has seen a definite outcome and the fact that Wigner can assign a superposition state which doesn't include the fact that he's seen something.
Their focus is not the same as Wigner's, because somehow consciousness doesn't seem to play really a fundamental or a key role in these new works. Would you agree with this assessment?
I mean, I would say that the concept of observerhood, whatever that means, is necessary. So, what you have to assume is that there are entities in the universe that are capable of registering a single definite outcome of a quantum measurement, right? And that there's more than one such entity in the universe, right? So in some sense, you have to assume, a no solipsism, right? So I'm not the only conscious entity who can act on things in the universe. Other people can as well. So to that extent, but it's not about the nature of consciousness. It's about the nature of reality.
What would you say about people's understanding of the word reality? Because a priori, it's not clear to me that everybody understands the word in the same way, and
it certainly isn't. And yeah, I mean, you have to distinguish, of course, philosophical concepts from technical things in theorems, right? So sometimes in the foundations of quantum mechanics, things go under the name realism that can be very different from, philosophically what's thought of as scientific realism. So, I mean, I have a particular take on it. If you want me to go into that, I can. But
sure.
Okay, it may take us a little bit further afield. So, I mean, personally, I have no doubt that there is an external world, right? But the question is, what's its relationship to our scientific theories? According to the scientific realist view, our scientific theories should at least be attempting to describe some reality that's out there independent of us. Now, exactly how you couch that, what you're realist about. Are you going to be realist about objects, entities, theoretical description, structure, various things? There are various different kinds of realism from the philosophical point of view. But the basic point is that there's something out there. And one of the reasons why people believe in realism, though there are several, but one of the sort of philosophical arguments, which is due to Hilary Putnam, it's called the no miracles argument. Right? So the idea is that our scientific theories are very successful. If they weren't actually true, right? If there weren't actually some world out there that actually follows these laws and makes them true, how would we explain that success? Like, what reason would we have to believe that, the scientific theories would continue to be accurate? So to some degree, like if you're going to be a scientist at all, you have to at least sort of believe in some kind of scientific realism, because otherwise, why would you do it? Right? So if you didn't have any grounds to think that you were really getting at sort of deep truths about reality. So, it seems like a popular position. On the other hand, you have the point of view which says, which comes more from the sort of idealism type of point of view, which sort of says, well, the only thing that we actually have access to are our own sensations. That's the only thing you have direct access to, right? There's sort of nothing objective out there, and there's nothing objective in anything that we see, because it's always filtered through our sense experiences. So from this point of view, you might say, well, a theory, scientific theory, is nothing but some kind of summary of sense experiences. This is the philosophical meaning of the realism, anti-realism debate. So where do I stand on that? I mean, I don't really stand anywhere on it. I think I take a different kind of point of view, which is, okay, I do believe there's a reality out there. Now, what does it mean? What does it mean for something to be a true statement about reality? I don't know. There are various philosophical theories on that. However, there are various things that might be true of the world that, if they are true, they aren't scientific truths, right? So if it just happens to be the case that there's something in the world that never interacts with anything that we could ever have an experience of in any way whatsoever, if it's there, then there are true statements about it. However, I wouldn't call those statements scientific, right? Because science is explicitly supposed to deal with things that are related in some way to, the way that we observe the world, the way that we interact with the world, right? So I want to put to one side the question of, whether there is, some fundamental truth that's different from the notion of scientific truth. They may or they may not be. But one thing that scientific truths have to have is they have to have some kind of utility, usefulness. This basically makes me a pragmatist about scientific truth, right? Because in the pragmatist conception, roughly speaking, something is true if it's useful. Okay. Now, that's usually thought of as kind of an anti-realist type of view, but it's really not completely anti-realist like that. Why would something be useful? Well, in part, it has to be because it's reflective of part of the way the world is, right? If something wasn't reflective of the way the world is in some way, then it's very unlikely to be useful, because you'd have no reason to trust it as reliable in a sort of for all time, as our physical laws seem to be. So it's not completely anti-realist. And I also want to say I'm very sort of broad in my conception of what I mean by utility. If I have two descriptions of the world, and they make the exact same predictions, but one of them allows me to reason about the world far more quickly or efficiently than the other one, then I would also say that that's a type of utility, right? So I don't mean to couch utility purely in terms of in what you can predict. So from this point of view, I would say that scientific realism about the theories that you're talking about has value because it's explanatory, because it has some utility, right? So in almost every other theory of physics other than quantum mechanics, this is sort of uncontested, right? When I'm doing classical electromagnetics, then I think of the electrons as real particles that exist and they're going around on trajectories. And that's the thing I'm trying to explain. And that's the picture I have in my mind when I'm calculating. Now, you could certainly say, okay, that's just a fiction, right? The only thing that really exists is, the marks on photographic plates and stuff like that. But if you really try to reason with that picture, you'd have a very difficult time thinking about electromagnetism or thinking about how electrons should act in new circumstances that you haven't encountered before. Whereas the picture of these things really existing and really having trajectories and fields really being out there is much more useful, much more helpful. If you have that picture in your mind, you're going to be sort of much more efficient and much more accurate in your reasoning about the world. So, I think that scientific realism as an idea has pragmatic cash value. Now, that's not to say that it has to be true, right? Because we could encounter a theory like quantum mechanics, which presents difficulties. And then if you have this sort of pragmatic conception of truth, it's not necessarily the case that scientific realism has to be true. But if we're going to give it up, we have to give it up for something that's more useful, right? So the question here is, if I adopt the sort of realist views of quantum theory, if I can come up with a realist view of quantum theory, then in some sense I would expect that to be better, because I'm used to thinking that reasoning in terms of things that actually exist is better or more useful than not doing so. But on the other hand, I have to introduce some kind of weird ideas in order to get that to work in quantum mechanics. So some other people might argue, well, it actually has more value to not do that. And this is showing us that in this particular case, it would be better to take an anti-realist or at least not so full-blooded realist stance towards quantum mechanics. Now, I say all this because it's like, to me, it's not a question of I'm not questioning whether our scientific theories really represent reality or not. This is sort of an internal question about the theory. It's about sort of what's the better explanation? Which view is going to give us more explanatory power?
Here you're posing two possible criteria on what's a good theory for natural science. It's about predictions, making correct predictions first, and then it's also about having a good understanding. Of course, if we have a theory meets both criteria, then that will be the answer. Question arises if we have maybe a theory A that gives the correct predictions in all cases, but it's not very intuitive. And we could have a theory B that doesn't give the correct predictions for all experiments. Fails in some cases, but it's very intuitive. It's very efficient for reasoning. In this case, perhaps we need to make a choice. Do you have a preference?
This question is more tricky than you might think, because, a lot of people, like if you're naive about it, you'd say, well, of course, you're interested in just making the most accurate predictions per se. But quite often it's the case that we'll prefer to work with a simpler theory, because you don't need the predictions at such a fine-grained level of detail, and the less predictive theory has a simpler explanatory structure that you can understand how to apply. So I wouldn't say it's one or the other. The other thing I would say, though, is that the line is not as clear as it might seem. So in the case of quantum mechanics, a lot of people will say this. They'll say, okay, there's the predictions of quantum mechanics, which we all agree on. And then there's this stuff called interpretations of quantum mechanics, which is just sort of a bunch of different explanations which ultimately give you the exact same predictions. So, why waste your time trying to choose between them? To my mind, there isn't such a distinction, though. Like, it's funny because in physics, we really only make this distinction when it comes to quantum theory. Like, nobody says, well, there's the subject of classical mechanics, and then there's the interpretation of classical mechanics. No, it's not just unified as one subject. Like, we accept that ways of thinking about classical mechanics are, as important as the predictions it makes. So part of the reason why I say this is that when we say that two theories have the exact same predictions, that's only within a context, right? So we might be talking about, in the case of quantum mechanics, we might be talking about sort of the ordinary non-relativistic quantum mechanics of atoms, for instance. And then you can sort of fairly clearly say, yeah, all of these interpretations make the same predictions. Fine. Okay. Then you might go to quantum field theory, we introduce relativity and look at experiments in high energy detectors, and you might say, okay, it's the same there. It's like, okay, what about regimes that we haven't gone into yet? Like, maybe, the thing is, like, all of these interpretations, they make the same predictions as far as we've seen so far, but they give very different intuitions as to what the theory is fundamentally about. So if you are trying to develop a theory of quantum gravity, for instance, which is a theory that we don't know what it is yet, if you end up doing an interpretation that says, okay, quantum mechanics is about these state vectors that evolve in time, you might think, okay, that's the very fundamental thing that I have to start with. Or if you're adopting an approach which says, the most important thing is that something funny happens to the physical quantities, the observables, then that gives you a different intuition. So, and then, the specific interpretations, whether it be, collapse theories, de Broglie theory, they each give you sort of different ideas about how you might extend into this domain where we don't know how to apply a theory yet. So I would say that makes them, just because we don't know what the theory they're going to lead to is yet, doesn't mean that they're predictively equivalent. They're predictively equivalent within a certain context, within a certain domain. And I think that if you try to draw the line, like a very unambiguous line between the parts of a theory which make a difference to the predictions and the parts which are just sort of interpretation, I think you find it very, very difficult to draw that line precisely.
Now, coming back to the topic of extended Wigner's friend experiments, what do you think they add to the discussion of reality?
So, this is what I would say about extended Wigner's friend. So, we have a lot of no-go theorems in the foundations of quantum mechanics. These no-go theorems normally target wholesale the realist interpretations, right? Because they usually start, so I'm talking about things like Bell's theorem. All of these no-go theorems, they start off with a statement like, well, suppose there are some objective physical properties out there, and then they constrain how they have to behave. So, the implications of Bell's theorem are, of course, debated to this day, but nonetheless, they are constrained. They've told us that, interpretations of a certain type have to have superluminal influences in them. If you don't like the idea of there being superluminal influences, which you may well not like if you like the idea that Einstein's relativity is fundamental, then you can always respond to that by saying, yeah, well, I don't agree in your very first premise, like the idea that there exists some objective properties out there that are being probed by our experiments. And there's very little you can say against that point of view, right? What's the virtue of the extended Wigner's friend arguments is that they begin, like, to my mind, there are various things that they do, but to my mind, once you've gone out of this very sort of straight, full-blooded realist point of view of talking about properties of systems that objectively exist, these are really like the first results that constrain those kinds of points of view. The virtue of the Wigner's friend experiments is that they don't talk about the extended Wigner's friends experiments, that is that they don't talk about properties that exist independently of us. They only really talk about measurement outcomes, actually observed measurement outcomes and how they're related to one another. And yet still we get a constraint on the theory, so that there are constraints that apply to interpretations that are of the less than realist thought. They apply to a class of interpretations that I tend to call the Copenhagen-ish interpretations, in the sense that they bear some family resemblance to sort of the original views of the Copenhagen founders of quantum theory, like Bohr and Heisenberg and people like that.
Mentioned in your review article, there are several different extended Wigner's friend arguments. Would you like to explain to us some of these?
Yeah, so I think I want to start with something simple, right? So there are, so most of the extended Wigner's friend arguments are based on combining Wigner's friend with Bell experiments, okay? And that's where you get the strongest conclusions. But just like for intuition, I want to talk about something a bit simpler, which is just what happens when you repeatedly make a measurement and then Wigner undoes it. So first example of an argument like this in the literature is due to Shan Gao. I have a slightly different take on it, but I'm going to start even simpler than that. So let's just imagine that you have a system and it's prepared in some quantum state, and then you make a measurement of it. Okay. So then Wigner, according to Wigner, you're in a box, right? And he can come along and undo that measurement. And then once that's happened, you can go ahead and do the measurement again. So now you've done the same measurement twice. Okay. Now, here's the question. If you believe in the objective approach to Copenhagen interpretation, so there's a fact of the matter on each run of the experiment about what both these outcomes were. They exist together in the same universe, right? So there is also a relative frequency distribution, right? So we can say that that thing exists. So there's some joint probability distribution for the two outcomes. What is it? So here's some fairly intuitive cases. Suppose you happen to be measuring an observable for which the system is in an eigenstate. And that just means, by the way, in quantum mechanics, it's a measurement where you happen, there's always some measurement for which you know the outcome with certainty. So let's just suppose you happen to make that measurement. Okay, so in that case, you're going to get that one specific outcome. And then the measurement is undone. You're back to the initial state. You do it again. Of course, you have to get the same outcome because the individual probabilities are certain. So in that case, no matter how many times Wigner comes and you do the measurements and Wigner comes and undoes it, you're always going to get the same outcome in that case. Right. Okay. Now, let's consider the case where you don't do that. Let's consider the case where the probabilities are something more like 50-50. Okay. You might expect in that case that you should half the time get one of the outcomes and half the time get the other outcome. And there's nothing wrong with that. Maybe that's what happens. But the point is that in neither of these cases can anybody test that prediction, right? Because the only person who ever knew the measurement outcome gets their memory erased. So those predictions don't have to agree with any kind of quantum mechanical rule per se, right? Now, the individual measurements do, right? Because you could imagine doing this experiment in parallel. Like I have many different quantum systems all prepared the same way. I do the first measurements on all of them. Then I can check the relative frequencies of that and undo them, do the next one. I can check, the joint probabilities for all of the systems on an individual run before the undoing. So the sort of marginal probabilities should agree with quantum mechanics, but the joint probabilities, the sort of correlations across time, if they aren't predictable, well, quantum mechanics, first of all, generically just doesn't make predictions about correlations over time like that. Okay,
right.
There really isn't a quantum prediction. In this case, you might think, oh, well, okay, so the things should be independent and identically distributed, and so there's an intuition for what should happen. Okay, and you might say, okay, in the first case I described, all the outcomes should be the same. In the second case, they should be 50-50. And that's all fine as far as it goes. All I want to say is that if that's violated, it's not on pain of falsifying the theory because nobody can observe those joint probability violations. So now let's do something else. Let's consider an entangled state. So an entangled state is one in which there's perfect correlation according to some basis measurement. So, we often talk about spin up and spin down. So let's consider a situation where you have two particles and their spins are always aligned along the same direction. So you have like either up, up, or down, down. According to quantum mechanics, until the measurement is actually made, there isn't a fact about whether it's going to be up or down. Okay. So now let's imagine that we take one half of this system, one of the two particles, and we do the experiment that I described on it. So we repeatedly measure whether it's up or down, and then Wigner undoes our measurement. Okay, so that happens multiple times. Now, what's the intuition? You might think, well, there's no facts that, like, since I have this other entangled particle around, it should be like 50-50, right? You might think, because when I undo the measurement, I'm back to a state where there doesn't seem to be a fact of the matter about whether it's up or down. But this depends on what the other guy does. So let's suppose that the person who has the other spin could choose to measure it. And let's suppose we're always putting our Heisenberg cut in front of him because he's not the one whose measurement is being undone, right? So we describe him as his observations classically. So if he measures spin up versus spin down, suppose he does that before we start our experiment on the other side. Then my system ought to have collapsed into either spin up or spin down. And by the intuition I had before, when I make this measurement and repeatedly undo it, I should basically get the same, I should get the same outcome all the time, right? But this is suspiciously non-local, right? Because in the first case, when he didn't do that measurement, I said, well, it seems likely that it's 50-50. And in the other case, it seems, well, it has to be, on pain of violating quantum theory, it has to be all the same. But that depends on what's being done far away. Now, to some extent, this is obviously, you can experimentally verify this because these time-like correlations on the one side of the experiment where Wigner is aren't observable by anybody. So nobody will ever see the difference. But nonetheless, if you're an objective Copenhagen person, you're committed to the existence of these joint probability distributions. And you can see that it's hard to say what they are. In fact, as a Copenhagenist, you should probably be committed to the fact, you should probably be committed to your epistemic limitations, and you should probably say, well, yes, these things exist, but I refuse to say anything about what they are. Right.
Yeah, I see. Is it fair to say that nobody is really hurt by these extended Wigner's friend thought experiments? Because it seems so far only the objective Copenhagen interpretation is in tension with these arguments, but then nobody has to take these interpretations because textbook quantum theory doesn't really specify for you what you should really predict.
Yeah, I mean, it's kind of hard to say, right? From the first perspective of Copenhagenism, a large swath of physicists still would say, I believe the Copenhagen interpretation of something like that. If you inquire as to what their beliefs are, really, is there a limit to what can be described by quantum mechanics? Usually, no. In practice, maybe yes, but in principle, no. And so then to say, okay, but there are probabilities, real relative frequencies that exist that cannot be predicted by quantum mechanics, that I think should be a little bit disturbing. And then on the other hand, there are perspectival interpretations. Well, and I would put cubism and relational quantum mechanics in this category, which say, no, those facts are facts relative to something, right? They're facts from the perspective of some agent. As far as the friend inside the box is concerned, relative to him, from his perspective, there is a definite outcome. From Wigner's perspective, it's not just that it exists and he doesn't know what it is. It's that for him, there is no fact, right? No measurement outcome exists for him. So what exists is relative to your perspective in this point of view. You believe in this sort of proliferation of worlds. Okay, they all exist in the same universe, but they are relative to individual agents or systems. And, so you still have this kind of pluriverse that you do in the many worlds interpretation. That's also disturbing. So, my answer to the question of which interpretation is correct is always none of the above. And I think the conclusion here is that, if you were hoping to stay Copenhagenish in order to, make things sort of more clearly empiricist in a very hard-headed way, then you're barking up the wrong tree. It's not gonna help with that.
That's an interesting point, because it seems to be a very strong point to say that none of the interpretations is correct. you don't want to modulate your judgments by credences, for example, assign many word interpretation with a 1% credence of being right.
Let me say this. First of all, I'm not a believer in precise credences in this sense, right? So I don't believe that this is a situation into which Bayesian probability theory really applies. I'm certainly happy to say I think certain things are more likely than other things, or to sort of give comparative relations here. So long as we don't see violations of quantum mechanics, I tend to prefer interpretations that that make some kind of completeness assumption. So that means that of the things that exist, I prefer Copenhagenish interpretations, and I prefer many worlds to things like the Brye-Bohm theory and spontaneous collapse. If you want me to make a very strong prediction, I would say that I believe that spontaneous collapse theories will be ruled out in my lifetime.
Really?
Yeah, well, one of the reasons for that is that they can be ruled out because they're not actually, strictly speaking, empirically equivalent to quantum mechanics. They do say that collapses are definitely going to happen at some scale, and indeed you can do experiments. You can try and create macroscopic superpositions of a massive object in two locations. You can also get constraints from cosmology because the interpretations say that the conservation of energy is only approximate. So you can begin to narrow down the parameter space until the theories don't solve the measurement problem anymore. And although we're quite far away from doing that, over the years, the experimentally viable area has reduced. And there are not a huge number of people, but there are plenty of people working on these kind of experiments. And so my guess is that they'll be ruled out. I also, since I don't believe in the reality of the quantum state, so the idea that the way you fix things is by making it objectively collapse seems implausible to me in the first place. So I definitely put those close to the bottom of my ranking of how plausible.
On the other hand, you also mentioned many word interpretation.
Yeah.
This is another approach that takes the quantum state as reality, at least in
it takes reality. The reason why, I mean, so on some days my commitment to like a kind of full-blooded realism is stronger than my commitment to the unreality of the quantum state, in which case I may start to look at many worlds a little bit more favorably. But I also have slightly as a joke, at least thought out, an alternative version of the many worlds interpretation in which the quantum state isn't real. I mean, I don't know if it's a really appealing interpretation, but it's possible to take an Everett-like interpretation, or make an Everett-like interpretation in which there are many worlds, but there's no real quantum state. It's kind of a bizarre thing, and so probably I slightly prefer that to standard Everett at the present time, but details are still need to be worked out.
Well, how does that differ from the perspectival approaches?
Because in the perspectival approaches, only one measurement outcome ever exists for an observer. There aren't two copies of any observer, there's only ever one. In the many worlds interpretation, the entire world literally splits, and there are two copies of the world, two copies of every observer, and that's still happening in the sort of epistemic. I call it the ironic many worlds interpretation, by the way, because the only reason for believing in many worlds is if you believe in the literal reality of the quantum state, and the only reason for you're only a psi epistemicist if you psi epistemicists typically want to live in like a single universe. So you're taking the worst of both worlds and combining it together. But nonetheless, it does make some amount of sense when you try to put these things together.
That's it. So here's my understanding of your ranking system. Objective collapse model is lower than Everettian, which is in turn lower than ironic Everettian. Is that right?
Yeah, and then somehow that's sort of level with Copenhagenism. And then I have to say that things like De Broglie are in between. I like it better than spontaneous collapse, but I still don't really like having to have explicit non-locality. And then there's a huge gap, like so all of those really down the bottom, and then way at the top of my ranking, a long way at the top of my ranking with like probably 99% probability or something is none of the, well, I guess they're below now.
99%.
None of the other, I mean, at least 90%. I mean, as I said, I don't really think it's all that meaningful to give very precise numbers, but I want to give the impression that I think it's overwhelmingly likely that we're really missing something.
What's your reason to prefer this answer to the Copenhagen interpretation? Many of them also take an epistemic view on the quantum state, which you like.
Yeah, but I mean, really, I'd like to be realist, epistemic, single universe. But ultimately, what I really want is for everything to click. You get the feeling that when you have the right explanations in physics, everything just sort of clicks into place. And a lot of our interpretations today are more like, well, here's the fully formed theory, which you don't know what it means. How can I stick things onto it, if you like, in order to make it make sense? And it kind of feels like we don't have the right explanatory structure here.
I see. Would you say realism is one of the issues for the Copenhagen interpretations, or?
I mean, realism in the sense of, so usually when we talk about realism in quantum interpretation of quantum mechanics, we mean a sort of very full-blooded realism in which there's sort of some correspondence theory. Okay, so I have entities that exist in the formalism of the theory, and somehow they're in one-to-one correspondence with things that exist out there. That kind of realism certainly might go because it's already not the most popular kind of realism amongst philosophers of science in the first place at this point. But I don't think just throwing it out and not replacing it with something is good either. So, in Copenhagenism, we say, well, we're just going to throw that out. Well, by throwing that out, you also throw out a whole bunch of other useful things like the ability to analyze counterfactuals, the ability to analyze things in causal terms.
Right. Is it fair to say that on this aspect of realism, you disagree with some advocates of the Copenhagen interpretations because, according to them, cubism is a realist approach to quantum theory. Relational quantum mechanics is a realism approach to quantum theory.
Yeah, I mean, it's you have to be. I mean, obviously, things have different meanings in different contexts. I would say, okay, I get your point, but not in the way that most people in this field mean it when they say realism, right? So, cubism says that it adopts what they call it participatory realism. So the way that you know that the world is out there and independent of you is that when you kick it, it kicks back, right? And you're like, okay, I don't think anybody disagrees that that's what happens, but that's not what people usually mean when they say scientific realism. So you're using the word in a slightly different context. At the bottom of it, that's more or less a semantics issue. What you can tell is that they're noticeably different. They're giving up something that interpretations like spontaneous collapse and the Broglie theory have. They're definitely giving up something, and they're less. The reality is less objective. But I think that they also give up too much because you give up the ability to like really make something like a causal explanation of the Bell correlations, for instance, right? This is, there's some source which two particles come out and you make separate measurements. Really, that should have some kind of common cause explanation. The source should explain the correlations. And in sort of Copenhagenist interpretations, you largely just give up on the project of being able to do that. So, I think that probably the full-blooded realist interpretations assume too much, and the Copenhagenist interpretations assume too little about reality. And there's probably somewhere else in between that we can maybe find the right answer.
You mentioned you want something like clicks.
Yeah.
And this Copenhagenist interpretations does not match your standard because of, for example, they don't give a causal explanation.
Yeah.
Would you be, well, something clicks that feels like, one possibility is you only know it clicks when it clicks. The other possibility is you can run down a set of criteria before it clicks, and you know that.
Yeah, I mean, I don't want to be too rigid about criteria. I did write a sort of tongue-in-cheek blog post when I was much younger, which was about a set of criteria that interpretations should satisfy. And I almost immediately regretted it because people would send me emails saying, "Oh, here's my new interpretation. Here's how it fits all of your postulates. You now agree with me." And so, but if it clicks, it's going to be so much more useful to me than everything that we've got so far. The utility of interpretations in terms of being able to articulate the theory, being able to stretch it to new heights and to new regimes is really not very, well, at least it's not very well developed right now. By those days. There are a few people like Anthony Valentini and my own postdoc, Indrajit Sen, who are trying to use de Broglie theory to develop physics beyond present-day physics. I think that possibly the way forward is to really try and stretch interpretations of quantum mechanics and foundational ideas into areas where quantum theory might break, into things like quantum gravity or quantum field theory, where we don't exactly know how to apply these ideas, because that might break something. And, as I said, in the foundations of, one of the reasons why you study the foundations of a theory is that you think that there might be something wrong with them. And if you think that there might be something wrong with them, then they ought to break somewhere. So finding the breaking points is going to be key. Will it break in a way that really ends up resolving the debates on the foundations of quantum mechanics? That I'm hoping is true, but I have to say, like, my credence that will resolve the matters, I mean, it's a bit lower, like maybe down in sort of 20-30%. So I think there's like a chance. It's maybe not a major chance. Could be that people who are working on string theory and related things, if that's all correct, then nothing is really going to change about the fundamentals of quantum theory. So, I don't really want to say I'm sure. I would love it if foundations of quantum mechanics turn out to have something to do with like real future directions in physics.
Talking about future directions, what about Markus Mueller's ideas of a first-person perspective approach to physics?
Yeah, I mean, I guess that we'll probably talk about this a bit more on another occasion, but I'm not that convinced about it. I'm not necessarily that against trying to develop things from the first-person perspective. One of the things he tries to do in the work is explain why there would be the appearance of an outside world. You could argue that it's an explanation for, if there was an outside world, why would our theories, match it to some degree? So that aspect of it, it's interesting. However, I think that particular approach, I really don't like the idea that the world is founded on things that are like objective probability theories. I don't believe in any kind of objective chance or propensities. I'm pretty hardcore subjective Bayesian when it comes to that. And I think that founding any kind of sort of realistic, I mean it's in the colloquial sense now, not realist, but realistic approach to the construction of physical theories on something like algorithmic information theory, algorithmic probability theory, like he does. There's a phrase from a paper. I love to quote this phrase. I think it's Diaconis and Zabel. It's a Bayesian paper. Doesn't matter what the topic is, but they use this phrase a logician's parody of a complex psychological process. And that's kind of what I think about taking that approach too, because the idea that you could even formulate a physical theory precisely enough to like write it down as, say, a logical program with a length that can be defined. To my mind, things are more vague than that, and always will be more vague than that. So I think, I prefer accounts of this sort of stuff which are a little bit looser than allowed by his approach.